first law of thermodynamics equals to Q plus W. And so since that is 0, this is going to be equal to Q plus the work from, I guess, A to B. And so the work from A to B is negative Q. And so we need to figure out which Q this is. And, all right. So, again, go back to the piston. The temperature is staying the same. And typically to do anything, I got a system here that is sitting there fat, dumb, and happy. In order to get to do anything, I have to put energy into it. So basically that Q, since it's going in, it's going from some hot heat source. Energy going in, which is causing work. To happen to it, yep. It's technically negative. Because remember, this is the work done on the system. So negative here, because if the system is doing positive work, then negative work is being done to the system. All right, I might screw up a minus sign here, but we'll go with it. All right, from B to C. Adiabatic expansion. What's 0?
I just said it.
You said it before.
Change the temperature. Change the temperature.
No, actually, we're in this section right here, next section.
Okay.
Adiabatic expansion.
E.
Yes, Q is 0. So basically, we put heat into the system in this first segment, and then we turn the heater off, or somehow we get it so that Q goes to 0. And so my change in my thermal energy, it's got to be equal to, well, the work being done. So it's like create the energy into it, I put it on a burner, energy goes into the system, then I turn the burner off, so that all that's happening right now is sort of, I've got residual heat in here, particles moving faster, and they're still continuing to do work on it. I am going to stick with the way my notes are written. This is what I talked about, messing up the negative signs. If we define work 8B as the work done by the system, then that would be negative there. That becomes positive. And over here, expansion is still going on, so WBC would be the work being done by the system, so negative WBC is the work done on the system. The gas is expanding, therefore it is doing work. If it's doing work, it's losing energy, so my change in thermal energy should be a negative number. Now, I don't know if I did this next part. Let's see, I want to write down corner over here. Efficiency equals 1 minus Q C over Q. consistency here. All right. I think I did do this, but we'll run through it again. For the isothermal process. Nope, we'll come back to it. Sorry for changing my mind several times there. From C to D, isothermal, what's going to be 0?
Change in thermal energy.
Yep. All right, so in this section right here, we have QHN and we have WAB out. Over here, we have WBC out. Over here, so we got isothermal compression. I know that, so change in thermal energy is 0, which is equal to Q plus the work done on the system. My volume is shrinking, which means the piston is coming back down. So work is being done on the system. So this would be equal to Q plus WCD. And so Q in this process right here, so energy is coming out. So we have some excess heat that we're getting rid of, and work is being done on it, CD. So QC is equal to negative WC. And then in the last step, as we return back to our starting point, we have adiabatic compression. And again, what's equal to 0? Q. Yep. So energy, change in thermal energy is equal to work. All right, so the efficiency of this particular cycle, well, we got our formula over there. So my efficiency would be 1 minus QC over QH. And I know that QC is just the negative work being done in section CD. Now, the negative sign has already been taken into account, so it's 1 minus the WCD. The book does it by just sticking absolute value marks around the QC over WAB. So in an isothermal process, I know PV is equal to, doing the physics version, input times Boltzmann's constant times time, or times temperature. In here is the number of particles involved. We are assuming, obviously, an ideal gas. I know that the work done is equal to the work done on the system, negative PdV, which is negative integral in kVt over v dV from, well, in this case, we'll do it generically, from some initial volume to some final volume. Well, the temperature is constant, Boltzmann's constant is by name a constant, and the number of particles, we don't have any particles leaving this container. It is, I'd like to say airtight, gas tight. So in our particular case right there, work AB would be negative in kV. I don't know why I keep doing that. kVt, that's right, times the integral of dV over V from some initial volume to some final volume. What's the integral of dV over V? If I wrote it dx over x, would that help?
Is that ln v?
All right, natural log.
Yes.
So this is equal to negative n kV t natural log of V from some initial volume to some final volume, which is negative n kV t natural log of the final volume minus the natural log of the initial volume. Lost my minus sign. I can distribute the minus sign, combine my two log terms there, and I'm left with n kVt times the natural log of Vi over Vf. So temperature is constant in these two situations here. So, well, this is down the right. So when I'm talking about WAB here, we're in this region right here. We have energy being put into it through heat. So we're talking about whatever the high temperature is. At the compression, so from D to A, we're talking about whatever the low temperature is. So the work done by AB is going to be N kV times the high temperature times the natural log of the volume at A over the volume at D. Similarly, work dA is going to be N kVt cold times, oh, oops, wrong spot, over here. N kVt T cold times the natural log of the volume at C over the volume at D.
Is that VA over VD, or is it supposed to be V?
That should be B, thank you. And CD, all right. Any questions on this before I erase it? All right, so our efficiency then has been changed to 1 minus WCD down there. And just a moment. Oh, well, I wanted QC anyway, so that's N kV T cold times the natural log of the volume at C over the volume at D, divided by N kb T hot. Natural log V A over VB. Obviously, that will simplify. 1 minus the natural log of VC over VB over the natural log of VA over VB. I guess at this point, all my V's are going to be volume, so those are all capital V's. Ooh, I lost my TC and my TH. All right, so it comes down to what exactly is this? Well, I still have these adiabatic processes here that I haven't done anything with. So let's do something with them. In an adiabatic process, Q is equal to 0. I need another word. I'll use this one. If I have an adiabatic process, I know that the change in the thermal energy is equal to the work done on the system. Because again, Q is equal to 0. Sorry, Benjamin, you were glancing over there. Can you wait a little
I'm
longer?
just writing this last two things down. Alright, we're good.
And so if we went into the differential, then I know that work is equal to the negative integral of PdV. And obviously, one moment. All right. And this change in the thermal energy is equal to, I guess, if we went to differentials, the thermal. Notation sucks here. All right, try that one again. So generically that, if we look at the differential form of it, we get this, that's a W. This is going to be in the heat capacity for a constant volume, dt, and that's going to be equal to the negative integral of PdV. No, sorry, just the differential, negative PdV. Well, ideal gas law. So I have N times this constant, dt, is equal to negative nRT over V dV. And now we get common things on the like side. Well, first we get rid of N. I'm going to bring T over to this side, so I've got dt over T. is equal to negative R over CV times dV over V. Now R is a constant, that's the gas constant. CV is a constant for the material. There was another relationship with that we derived last week, that the heat capacity for a constant pressure minus the heat capacity with a constant volume is equal to R. So therefore, R, well, is equal to that. We can plug that in, so if I have R over CV, that's equal to CP minus CV over CV, which is CP minus CV, CP divided by CV minus 1, which is equal to gamma over 1. Gamma is just the ratio of CP to CV, and I'm pretty sure we did that last week as well. We are heading somewhere, it's not just random stuff. So this becomes dt over t is equal to negative gamma minus 1 times dV over V. Obviously, we can distribute the minus sign there, take the integral, and we end up with the natural log of t